So today we are going to talk a little bit about Lewis structures and neutral molecules. This is the arts and crafts portion of the unit, meaning you get to draw shapes and symbols and molecules basically. But before we get into the arts and crafts part of the unit, we need to kind of go back in time and talk about something that we definitely mentioned at the beginning of this at the beginning of the unit last unit, but it's been so long we may have forgotten. So the octet rule says that all atoms will want to satisfy the octet rule, and the way that they do that is by bonding, by either transferring electrons in an ionic bond, sharing electrons in a covalent bond. So all atoms want to have 8 valence electrons, and the way that the way that they do it is by bonding. But I want to kind of illustrate the point by going way back in time and talking about something that is not necessarily going to be part of this unit, but it might help you jog your memory. So last unit, we spent time talking about metals and nonmetals, and we said that, like, for example, sodium would have 1 valence electron, right? And if sodium has 1 valence electron, its electron configuration would be something like 1s2, 2s2, 2p6, 3s1. And chlorine's electron configuration would be something like 1s2, 2s2, 2p6, 3s2, 3p, I think it's 3p5. Yeah, sure, why not? 3p5. As of right now, sodium's 1 valence electron is this one right here. And chlorine's 7 valence electrons are these 2 plus 5, 7 right there. So what happens is that sodium transfers an electron to chlorine, right? And when it transfers an electron to chlorine, chlorine looks something like this. It's got the 1, 2, 3, 4, 5, 6, 7, and then it's got this other electron from, say, sodium, and then it gets a charge of like -1, and then sodium goes down and has a charge of +1. And then we drew those last semester. What we were getting at was like sodium achieved a stable arrangement of electrons, but we didn't really draw any stable arrangement of electrons. So I want to try to show you or illustrate the idea that this 1 electron transferred to the chlorine, right? And then it left sodium with 2 plus 6, which is 8 valence electrons. And then chlorine gained an electron, so now it has 2 plus 5 plus 1, so it has 8 valence electrons. And that's all the reason, that is the entire point and purpose behind atoms bonding with one another, is for them to get 8 valence electrons. So that's ionic. And in the covalent compounds, which is what we're going to spend the majority of this unit talking about, they don't transfer electrons, they share them, right? So of course, there's exceptions to every rule. So let's talk about those exceptions real quick once. And I'm going to start with helium. If I can write the word. Now, helium, its electron configuration is 1s2. Meaning that helium has 2 valence electrons. And that's it. Helium doesn't want 8 valence electrons. Helium wants 2 valence electrons. That's the rule. The reason why that's the case is the 1s2 is a full sublevel. It's a full energy level. We can't add any more to it. So we're not going to spend a lot of time talking about helium because we're never going to really bond with any helium, but that does allow us to have a conversation about hydrogen. Hydrogen's electron configuration is 1s1. And if I was to draw its structure, or its Lewis structure, it would be something, well, I'll do it like this. I'll do it over here. That. So hydrogen has 1 valence electron, but it wants to be like helium, so it will bond to have 2 valence electrons. So it will bond to have 2 valence electrons. And so what does that mean? It means that hydrogen has 1 valence electron. Hydrogen wants 2 valence electrons, hydrogen will bond one time only. And that is all. Okay. The next one we should talk about is beryllium. Its electron configuration is 1s2, 2s2. And so what that tells us is that beryllium looks something like this, right? So beryllium has 2 valence electrons. Okay. Which means it can bond or will bond 2 times. It wants 4 valence electrons only. So hydrogen wants 2, beryllium wants 4. The other one that we're going to be concerned about is boron, which is electron configuration 1s2, 2s2, 2p1. So boron looks like this. Boron has 3 valence electrons. It will bond 3 times. It wants 6 valence electrons only. So those are the really major exceptions to every atom wanting 8 valence electrons. And you're probably just going to have to know that. Now, the other thing about that is that the one that we're going to see the most often is hydrogen. Okay. So if any of these 3/4 are ones to really keep an eye on, hydrogen is the one we want to keep an eye on. All right. Moving along. Now I'm going to talk briefly about how to draw Lewis diagrams. So we drew Lewis structures for individual atoms. Now we're going to use Lewis structures and the rules for Lewis structures to help us draw molecules. Okay. So a couple of things. The first thing is that when you're given a structure or a molecule to draw, what you do is you simply take all of the valence electrons that are available and you throw them into a bank or a pot, and then those are the ones that you work with. It's kind of like when you go out to the dinner somewhere and they put the dinner on one ticket instead of like they splitting it amongst multiple people, and you're like, oh, what's my cut? And everybody just starts throwing 20s at the table. You know what I'm talking about? I don't. I usually just throw hundreds because that's how I roll. Pennies. 100 pennies at a time. Okay. But the truth of the matter is that when you settle up a bill, right, you put all of your cash in the middle of the table, and then that's what pays the bill, right? But all of that cash is contributed by everybody sitting at the table, and the same thing applies to the valence electrons. Every atom that's involved in the molecule contributes a very specific number of valence electrons, and that's all the electrons that you can use to draw the structure. Now, the next thing we need to talk about is figuring out our central atom. Now, there's a couple of ways that we can do that, and there's a couple of things to keep in mind of. So the central atom is usually the first atom in the chemical formula. Usually the first atom. If it's not the first atom, it could be a single element, like it would have no numbers behind it. One thing it can't be is it will never be hydrogen. Hydrogen will not be the central atom. And chances are, if you have carbon at all, chances are carbon will probably be the central atom. After you've figured out what your central atom is, you draw it. And then after you draw it, you go ahead and you take the rest of the atoms and you just kind of scatter them around, spread them out as far as you can from each other around the central atom. And then you just connect them with a line. And then you start adding electrons from the rest of the pot. And then you go from there until you've used all of your electrons. The easiest way for me to show you that or to talk through that is to go through like 3 or 4 examples, which is what we're going to do right now. So we're going to start with a really incredibly difficult one, H2. So in this instance, my formula is H2, and I know that I have 2 hydrogen atoms. Okay. Now, for the sake of argument, I'm going to collect my electrons in the electron bank the way that I'm going to do it here, and then I'm going to do it differently for the next few. So here we go. So in this instance, I have 2 hydrogen atoms. Each hydrogen atom, according to the handy-dandy periodic table, has 1 valence electron. And if I add them up, because that's all that I have a total of 2 valence electrons to find a home for. Now, because this compound only has 2 atoms in it, there's really difficult to figure out which one is the central atom because 2 things don't really have a center. 3 things do, 4 things do, but 2 things don't. It just becomes a line. So I'm going to make it a little bit easier by just simply drawing hydrogen next to hydrogen. Now, the next thing we need to talk about is how we connect them. And we've connected atoms already. We've done this already, but I guess we need to talk about it a little bit more detail. So we draw a line. That line is equal to 2 valence electrons. So every line you draw connecting atoms uses 2 electrons. Some people, when I do this in the beginning of the unit, I usually go like this. I say there's 1 electron and there's 2 electrons, right? And that helps because each line has 2 electrons. So if we go back to thinking about the Lewis structure for just hydrogen, 2 individual hydrogen atoms would look like this. And those are the 2 electrons that are involved in the bond. So how many electrons does hydrogen want in order to be satisfied? 8? 2, right? So if I look at this hydrogen atom, the one on the left, right? That line is 2 electrons that are shared for that hydrogen atom. So the hydrogen atom on the left has 2 electrons. It's satisfied and happy. The one on the right also has 2 electrons, satisfied and happy. Because it's sharing the electrons in the bond. Does that make a little bit of sense? Ish, maybe. The next thing we're going to be asking you to do is we're going to be asking you to identify what type of bond is present here. So I know that I have a hydrogen and a hydrogen, and when I go to calculate the electronegativity difference, according to the periodic table, hydrogen's electronegativity is 2.1, so 2.1 minus 2.1 gives me an electronegativity, a fat electronegativity of 0.0. 0.0 tells me it is a non-polar covalent bond. So it's a non-polar covalent bond. So the bond in between the 2 hydrogens is non-polar, which means the electrons are shared equally. So I do not have to draw arrows or partial charges, delta positive, delta negative. So far, so good. All right, now we clearly have one that's a little bit more complicated. I see, according to my chemical formula, that I have N1H3. So here's how I'm going to set my bank up. I'm going to say that nitrogen, and I've got hydrogen. I have specifically one nitrogen times how many valence electrons does nitrogen have according to the periodic table? So when you're looking at your periodic table, how many valence electrons does it have? Does not have one. It has 5, right? Nitrogen is in column 15. It has 5 valence electrons with a charge of -3, right? So nitrogen has 5 valence electrons. So 1 times 5 is 5 valence electrons. Hydrogen, on the other hand, we have 3 of them. And hydrogen has how many valence electrons? 1. 1 valence electron, I figured. So now we have 1 times 3, which is 3 valence electrons total. We're going to add that up for 8 total valence electrons. Okay, now I have only 8 electrons to play with to make sure that all 4 of these elements are happy. So I'm going to start with trying to figure out what my central atom is. My central atom is usually the first atom in the chemical formula, or it's the atom that's only one of them. And in this case, nitrogen happens to be both of those things. So I'm going to draw nitrogen here. The next thing I'm going to do is I'm going to go ahead and I'm going to draw or add the other atoms to the central atom. So in this case, I have 3 hydrogens. So I'm going to go hydrogen, hydrogen, hydrogen to the central atom. Then going to bond by drawing a line. So at this point, one line is how many electrons? 2. And I've used 3 lines, so it's 2 plus 2 plus 2. So I've used 6 total electrons. So 8 minus 6 is 2 valence electrons left over. Now, I've got to use those 2 electrons, but I got to figure out where to put them. So before I go much further, I'm going to look at my hydrogens. And what do I know about hydrogen? How many valence electrons does hydrogen want in order to be satisfied? 2, right? Hydrogen wants 2. And in this particular instance, the hydrogen on the left has 2 electrons, right? Because it's involved in one bond. And the hydrogen on the bottom has 2 electrons because it's involved in one bond. And the hydrogen on the left has got 2 electrons because it's involved in one bond. Nitrogen, on the other hand, has how many electrons around it right now? Has 6. Hydrogen is involved in 1, 2, 3 bonds, 2 plus 2 plus 2, right? So that's 6. I have 2 more electrons, so I'm going to give them to nitrogen just like that. So now nitrogen has its 8 valence electrons. It has 2 in the forms of dots, and it has 6 in the forms of individual bonds or lines. So everybody's happy. So we now need to identify, that's actually the correct structure. We now need to identify the what type of bond is present. So I have a nitrogen and I have a hydrogen bond. So I'm going to go ahead and locate nitrogen on the periodic table and identify that nitrogen's electronegativity is 3.0 and hydrogen's electronegativity is 2.1. 3.0 minus 2.1 gives me something like 0.9er for my electronegativity difference. That tells me that it is a polar covalent bond. And if it's a polar covalent bond, I have to draw the dipole arrow and I have to draw the partial charges. Now, in a polar covalent bond, the arrow is pointed toward the more electronegative element. So out of the 2, nitrogen and hydrogen, which is the more electronegative element? The answer is nitrogen. Good. So I'm going to draw my arrow toward nitrogen. So that would look something like this. And I have to draw 3 arrows because there's 3 bonds with nitrogen and hydrogen. I don't know, maybe it'd be helpful if we did that too. Okay. Now, the next thing we have to do is we have to add our partial charges. And remember back from this, like feels like forever ago, delta negative meant electrons toward, and delta positive meant electrons away. Okay. Now, in this case here, the hydrogen is where the electrons are being pulled away from. So these are all going to be delta positive, like that, which means that nitrogen will be delta negative. And in theory, you should probably draw 3 delta negatives, but like it's kind of overkill because it's the same. Questions about this so far? All right, here's what we're going to do. I'm going to give you this one to do. Ready, set, go. Now, I'm going to pause at this point. I'm going to do little checkpoints here, okay? My electron bank, I came up with 32 valence electrons total. There was one carbon, which has 4 valence electrons, and there were 4 chlorines, which have 7 valence electrons. 4 times 7 is 28. 28 and 4 is 32. Okay? Carry on. So now, little checkpoint. I identified carbon to be my central atom, and I bonded the chlorines to my central atom. At this point, how many electrons have been used total? Correct. Somebody said 8. So the answer, every line is 2 electrons. There's 4 lines, so I used 8. So I'm going to subtract 8, and I'm going to be left with 24 electrons to find a home for. Go ahead and finish this one up. So because carbon had 4 lines around it, right, it had a total of 8 electrons. So carbon had satisfied the octet rule with just those 4 bonds. Okay. Chlorine, say the chlorine on the right, for example, had 1 bond. That 1 bond, right, only gave chlorine 2 electrons. So I needed to start adding electrons to each chlorine because prior to doing that, each chlorine only had 2 total electrons. So I added 6 electrons to each chlorine, using up all of my 24. Now, every chlorine has 8 valence electrons, 2 from a line and 6 from dots. Does that make sense? Good. So now what we're going to do is we're going to go ahead and calculate the electronegativity difference here between carbon and chlorine. So I know that carbon's electronegativity, according to the periodic table, is 2.5, and chlorine's electronegativity, according to the periodic table, is 3.0. Math says that's going to be 0.5, which tells me that this will be nope, I lied. It will be polar, covalent, bond. So each of the bonds between carbon and chlorine, carbon and chlorine, carbon and chlorine, carbon and chlorine are polar covalent. Now, if they're polar covalent, we have to draw the dipole arrow, and the dipole arrow is pointing toward the more electronegative atom. And so according to my information, it should be something like that. So on each of these bonds, I'm going to draw this. And then lastly, I'm going to go and I'm going to add the delta positive, delta negative, right? So the delta negative is the side of the bond where the electrons are being pulled toward. So these are all going to be delta negative. And the delta positive is the side of the bond where all the electrons are being pulled away. So I only need to add one. So I'm going to put it right there because it's all the same type of bond. So far, so good. Now you got one more wrinkle to throw at you. One more example. The next example is, what do you do if you don't have enough electrons? I'm going to show you. So here we got the O2. It's oxygen, right? And there's two of them. So I'm going to draw oxygen. Nope. I'm going to draw oxygen. I'm going to say that there's two oxygens times oxygen has 6 valence electrons. So 6 valence electrons gives me 12 valence electrons. And I can't really do much more of that. So it's going to really be 12 valence electrons total. Now, because there's only 2 atoms involved in this situation, I'm going to simply connect them together because there's really no central atom. And I'm going to start by drawing a line for a bond, right? So at that point, I've used 2 electrons. So I'm left with 10 valence electrons to find a home for. And at this point, the only thing I can do is just start adding electrons until I've used them all in pairs. So it doesn't matter where you start, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if I look at the oxygen on the right-hand side there, that oxygen has 2 electrons in the form of a bond and 6 electrons in the form of dots, right? That oxygen is satisfied. It has all the electrons it can handle. The oxygen on the left-hand side has 2 electrons in the form of dots and 6 electrons in the form of, 4 electrons in the form of dots. So it only has 6 electrons. And when that's the case, this doesn't work. And I can't go to the bank and borrow more electrons because I've used all 10 of them. So I have to do something else. So what I'm going to do is I'm going to go and I'm going to add something called a multiple bond. And the way that I'm going to do that is I'm going to take 2 of the electrons, it doesn't matter which ones, and I'm going to force them to become a bond right here. What that's going to look like is this. Two bonds. Now, of those 2 bonds, right, I've used 4 electrons out of 12. Does that make sense? Because I'm redrawing this structure. So if I take 12 minus 4, I get 8. So I'm going to go ahead and continue adding 8 electrons until everybody's satisfied. So if I do this, and I'm going to redraw, I'm not going to, so the reason why I just put 2 on one and 2 on the other for my 8 is because I had already had that drawn before. Does that make sense? I had 6 and I had 2, so I just kind of like shifted 2 of the 6 to become a bond. So now at this point, the oxygen on the right has 4 electrons in the form of 2 bonds and 4 electrons in the form of dots. And the oxygen on the left has 4 electrons in the form of 2 bonds and 4 electrons in the form of dots, right? So at that point, both oxygens have 8 valence electrons and they're satisfied. So now we have to figure out electronegativity. So oxygen is 3.5 minus 3.5. And when I calculate that out, I get 0.0, which tells me that it is a non-polar covalent bond. nonpolar covalent bond. So what that means is that I don't have to draw an arrow because the electrons are being shared equally. And that wraps up basic Lewis structures for neutral molecules. Questions? Okay, if you have any further questions about this, make sure you talk to me about it. Otherwise, it's homework time.